there, welcome to our series of videos here. A little quick introduction into how we describe motion. Pudding's here to help us tonight, just because Cat. But this is all about kind of learning some of the ways in physics that we take actual objects and the way that they're moving in our real world, Cat, and trying to represent them in a more simplified fashion, just sort of on paper. So the concepts that we're talking about in this particular chapter, not exactly difficult concepts, but it's a lot of foundation work in terms of how do we represent it, sort of kind of rearranging how our brain is picturing movement and how we record movement. And then a couple of different stylistic things that we do, like writing motion diagrams or particle diagrams, and then interpreting graphs. Kind of a big part of what's happening in this particular chapter. And we're just doing like simple linear motion in here. And literally when I say linear, I'm talking about literally like y-axis only kind of thing, or x-axis only. We're not even going to be turning yet. We'll get into the next chapter with that kind of stuff. But this is really just about, like I said, foundational issues about how do we represent motion. So over the period, I think I've kind of split this into like 3 or 4 little shorter videos. That's kind of the stuff that we're going to end up doing. In this particular one right here, we're going to really be looking at motion diagrams and sort of reading, I guess, motion diagrams and sort of being able to interpret some information from them. In the next video or 2, actually, we talk about motion as a vector and the concept of vectors versus scalars. And then we really get into interpreting position time graphs. Last but not least, we'll do a little bit on calculating velocity, just the math application of the very simple formula, and just sort of get used to some of the conventions and what it looks like here in a physics situation. Like I said, none of these concepts are particularly challenging, but it's sort of setting that groundwork so that we can move faster ahead in later units. So first question is, I guess, what's a motion diagram? We're trying to talk about, like, how do we represent how something's moving? And a great way to picture it in your head is kind of like if you took a bunch of still frame photographs of something that was moving, and where is that object every time it moves? So you can think about the pictures at the top here about this person that's running, right? There's 1, 2, 3, 4, 5 little photographs of, like, a tenth of a second every time you take a snapshot of where that person is. How do we represent that motion in a simpler way so that we can actually manipulate that motion? And you've seen, with videos and things like that we have now, our motion capture technology is actually quite good. So how do we simplify that in a way that makes sense sort of on paper, so to speak? And so what we're going to use is something, like I said, called a motion diagram. We're actually going to simplify it a little bit, even smaller than that. So this here is an image of a person who's running. When we do these things, for right now, we're simply going to be talking about straight line motion. We're not going to talk about, what if they turn left in the middle of this? Really, all you can see in this is someone just running literally from left to right or right to left, however you want to call it, across the screen. And again, think of it like a series of snapshots over time. And if we overlay those snapshots on top of each other, you get an image like this one here at the bottom, where you can kind of get an idea of where this individual is for every, say, 1 second interval. Maybe 1 second is a little bit too long. Maybe it's a tenth of a second, but you could say that this would represent where this individual was. And if we were trying to do this, by hand, maybe it would be more of, you've got, person number 1 and then person number 2, and then, person number 3 is moving over like this. Where literally you're doing just crappy little drawings to show how this person is moving through time. So what you actually have here, again, is 2 dimensions. You have the person's position, where they are, and you also have time, because each particular shot represents a certain interval of time. In this case, it said 1 second or 0.1 second, whatever it is, but it's sort of assumed that each photograph is taken in the same amount of time. So you can get some information about how the person is moving from these 2 factors, how far they've moved, and how often those pictures are taken. You can get an image of how quickly they're moving, or are they moving smoothly, or are they moving, in sort of a more jerky kind of a motion. So these things, like I said, are called motion diagrams. Rather than trying to draw, the person running every single time, like if this was a car that was moving, we tend to simplify it even further. So here we've got these little orange cars that are moving across here. Rather than if I was going to ask you to make a drawing of this and try to actually draw a car every single time, what we do is something called a particle model. Now, a particle model is a type of a motion diagram, and a motion diagram is just a way of representing how something's moving from separate intervals of time. But now we're going to simplify it even further by saying, hey, we're just going to represent the car with a dot. A particle. That's why it's called the particle model. Kind of makes sense, right? And what this means is that instead of trying to draw a car every time, we're going to draw a dot. Now that dot has got to be someplace consistent on the car. That makes sense. Like here, they're drawing the dot sort of in the center of gravity, or sort of equal to the center of the car. But you could just as easily have said, hey, I want my dot to be every time here on the nose of the car. Or it could have been, the center of the front wheel. Whatever is easy, it doesn't really matter. You're just trying to represent the item with a single dot. And you can see what you've got here is a series of arrows now that represent this object's motion through time. So it is still a motion diagram where you can see that from this spot to this spot, let's say that's a second. And then from here to here is a second. And then there's a third second, right? If each one of those dots represents a time interval, then you can see that in this case, the car is actually speeding up, right? It's covering this much distance in the first time interval. In the second one, it's gone further. And in the third one, it's gone further yet. So now not only can you tell the direction the car is moving, that way, and you can also tell that the amount of distance it's going in each second is getting faster. So you know something about the motion. Again, so this is called a particle model, where it simply has a series of dots to represent an instant of time, an object at different places at an instant of time. So if you think about it now, we can really, really kind of divorce this entirely from the actual items itself. So if we wanted to talk about how something was moving, I'm going to draw a series of particle models. Now, particle diagrams or particle models for this literally is just going to be a series of dots. And we're going to sort of assume that every time I make a dot, that we can say that's a second. Or we can say that that's 3 seconds or 5 seconds or a tenth of a second. It doesn't really matter. So think about these two types of particle models, these two motion diagrams, constant speed slow versus constant speed fast. Now think about if you're taking two snapshots, snapshot number 1 at time 0 and snapshot number 2 at time equals 1. If that object is going slow, how far is it going to move every second? Versus if it's moving fast, how far is it going to move every second? So think about how close together your dots are going to be. I've got a series of dots written up here. What if I had dots that were more like this? Which of those would be more likely to represent an object that's moving fast, right? Well, you guys know this. If you're moving quickly, you're covering a lot of distance in a small amount of time. And if you're moving slowly, you're only covering a tiny amount of distance in the same amount of time. So if we do 5 seconds, I could do their second number 1, second number 2, second number 3, second number 4, second number 5. That would be constant speed and slow because you're not going very far every second. As opposed to constant speed fast, there's 1 second, there's 2 seconds, there's 3 seconds, there's 4 seconds, and then there's 5 seconds. And I'm trying to make sure that each of my little spots here is the same distance apart because we can represent the amount of space that's being covered by a little arrow, right? From 1 to 2. So we can go like an arrow like that. And I'm trying to make sure that all of my arrows are basically the same size. I'm actually previewing this concept of what we call vectors later on, but I can represent this object's motion with an arrow. So a short arrow means it's a small amount of distance. Long arrow is a lot of distance, right? So interpreting motion diagrams, if you take a look at it, you can really tell kind of how something's moving. So if we want to do it with a little bit more, acceleration to it, if it's changing speed and getting faster, think about now how those dots are going to be spaced out. Are the dots going to be staying the same distance apart? Are they going to be getting further apart? Or are they going to be getting closer together? Every series of dot. Remember, every dot equals like a second. It's a time interval. So if it's changing speed and getting faster, that means if it's starting off kind of slow, right? But as it's getting faster, what do we see? Well, we see these dots starting to get a little bit further apart, right? And this would be something that would be accelerating, where each interval of time has a greater interval of distance. And we could see that by looking at our little arrows here, which would be getting progressively longer as we went. So now you should be able to kind of in your head envision, maybe sketch it out on a piece of paper. What would it look like if it was changing speed slower, right? And getting slower. Well, if it was starting off fast, right? Something like that, it's going to be getting closer together like that. And we can even say that how quickly those dots get closer together, sort of like that rate of acceleration. Is it accelerating slowly or is it decelerating really fast? Like here it would be like, coming to a stop, right? It is done. And this would be holding still, right? Just dots in the same spot, right? It's not even moving at all. So you can see a lot from these motion diagrams just in terms of things behavior. So again, a motion diagram is simply a way for us to represent something's motion in a linear sense. Again, we're not trying to do anything fancy, two-dimensional or anything like that. But if we turn it into a particle model, single dots, and assume that each dot equals an interval, a time interval, we can really start to interpret a lot about how that thing is moving, speeding up, slowing down, holding still, going a constant rate, going fast, going slow. So again, a particle model is one way that we're going to be interpreting something's motion. And then we can take these particle models and turn it into these little vectors, that these little vectors here would kind of represent how far did something travel in a particular interval of time. So there you go. That's the first video for tonight. And I'll do another one here in just a second. I hope that helped for you. See you in a bit. Bye. I can find where the stop is.